New, clear your schedule. It's time for radioactivity. Welcome to Flash Revision Lab. I'm your tutor, and we'll master this topic in a flash. Today we'll be exploring the fascinating world of radioactive decay. Let's begin by understanding that some atomic nuclei are not stable. These unstable nuclei emit radiation while they transform into more stable forms, and we call this process radioactive decay. Before we jump into the types of radiation, let's understand that radioactive decay is random and spontaneous. This means that we can't predict exactly when a specific nucleus will decay, and you cannot cause or influence the decay. The rate at which this all happens is called activity, and we measure it in becquerels, or BQ for short. Now, two important concepts to grasp are the terms penetrating power and ionizing power. Penetrating power refers to how easily radiation can pass through materials, while ionizing power is the ability of radiation to knock electrons off atoms, creating charged particles called ions. We can use these terms to describe the three main types of nuclear radiation released during radioactive decay. Let's break them down one by one. The first are alpha particles, which are a small bundle made up of 2 neutrons and 2 protons, with a mass number of 4 and a proton number of 2. These particles are actually the same as helium nuclei, which have a charge of +2. They don't travel far and can't penetrate materials very well, but they excel at knocking electrons off atoms. Alpha particles can't pass through paper, card, or a few centimeters of air. Now, beta particles are high-speed electrons ejected from the nucleus when a neutron changes into a proton. With a mass number of 0 and a proton number of -1, they have the ability to travel farther than alpha particles and can penetrate materials to a moderate extent. They're also pretty good at ionizing atoms, but not as good as gamma radiation. Beta radiation is stopped by aluminium. As for gamma rays, these are not particles but a form of electromagnetic radiation, like visible light, but much more energetic. With no mass number or proton number, they originate from the nucleus and boast an impressive ability to penetrate materials. However, when it comes to ionizing atoms, they're not as effective as alpha and beta particles. To stop gamma rays, you need thick lead or concrete. Now let's dive into nuclear equations, which help us represent and understand radioactive decay processes. To write a nuclear equation, we'll show the initial and final elements, as well as any particles released during the decay, and we'll indicate their mass numbers and proton numbers. For our first example, let's examine a uranium-238 atom undergoing alpha decay. Uranium has a mass number of 238 and a proton number of 92. When this decay occurs, it loses 2 protons and 2 neutrons, transforming into a thorium-234 atom, which has a mass number of 234 and a proton number of 90. Meanwhile, an alpha particle with a mass number of 4 and a proton number of 2 is released in the process. You can always check if your equation is correct by checking if the mass numbers and proton numbers add up. Here's another example for you: a carbon-14 nucleus experiencing beta decay. Carbon-14 has a mass number of 14 and a proton number of 6. In this case, one of its neutrons changes into a proton, turning the carbon-14 into nitrogen-14, which has a mass number of 14 and a proton number of 7. A beta particle with a mass number of 0 and a proton number of -1 is released during the decay. Now to check, we can add 0 to 14, which gives us 14, and adding 7 to -1 gives us 6, which tells us all the numbers in this equation are balanced. Now, you might be wondering what happens when a gamma ray is released during radioactive decay. When a nucleus emits gamma radiation, there isn't a change in the number of protons or neutrons. Instead, the nucleus transitions from a higher energy state to a lower energy state, becoming more stable in the process. So, in a nuclear equation involving gamma emission, the element remains the same, but the nucleus loses some energy, which is released as a gamma ray. And that's a wrap on radioactivity and radioactive decay. Thanks for joining me at Flash Revision Lab. If you found this video helpful, don't forget to like, subscribe, and hit that notification bell for more rapid revision content. If you have questions or need extra help, drop a comment below or reach out to us on our social media channels. Remember, with Flash Revision Lab, you're just a flash away from acing your exams. Until next time, happy revising.